So today I want to start off with questions about chapter 15. Then we'll go over the few slides I have on chapter 16, and then we can go over homework questions on chapter 16. So it's kind of our 3 items of business for today. After we do our mid-break, we'll talk calendaring. If you have any questions about that. Let me do say that on the chapter 15 homework that Melissa jumped on a little bit earlier, and Kimberly sent me an email about a certain item, and all of those things were resolved by me increasing the margin of error on a lot of the answer boxes on chapter 15 homework. There's several different spots where if you round to only 2 decimal places and you're off by 1/10, there's in the first step, and then the second step and the third step, you end up being off by 3/10. So I needed to increase the margin of error on the data entry boxes for the assignment. So it's not necessarily that you were doing it wrong. I just needed to increase the tolerance on those answer boxes because it's just how you rounded at which stage for several of those. So if anyone has any questions about homework, let's start with chapter 15, section A. Does anyone have any questions about the section A?
I have just on
the
within subject, the hand calculations. So the degrees of freedom within is supposed to be like the number of rows.
The total sample size within should be total sample size minus number of rows.
That's what I did wrong because I read that as NR.
Oh, it's NT.
And I was like the number of rows,
yeah.
Okay.
If it's number of rows, it'll just be the letter R. NT is the number total, like the number of scores total.
Okay, and then K in this instance is going to be 4, correct?
You want to share your screen so I can see exactly where you're at?
Yes. Sorry.
No, we just want to make sure we get everyone on the same page, including myself.
Yeah. Sure. Sorry about that.
Okay, here it comes. All right.
So just this portion right here.
So this is problem number 15A.
Number 4.
Number 4, part A. So the repeated measures. Okay, yeah, so the within subject. So NT in this problem, you have 8 subjects, but each subject has 4 different repeats. They're repeated under marijuana, amphetamines, Valium, and alcohol. So the NT is 8 times 4.
Okay.
Which is 32. 32 subtract 4 would be 28.
Oh, 8 times 4?
So we have 8 subjects. If you read the top of the question, we have 8 subjects, but they each did each of the 4 drugs. So everyone went through all 4 drugs. So the number that we have total is 8 times 4. We have 8 times 4 scores because we have 4 scores for each person. So NT is not the total people, but the total number of scores.
Okay.
Yeah.
Okay, that makes sense. And then, yeah, because I did the first calculation accurate. So once then just one more quick question. K and C, are those the same thing in this instance?
What, K?
Like in the formula?
K and C, yes. For a repeated measure, yeah.
Okay. Awesome.
Yeah. So the blue boxes there that are for within, those were defined when we were doing one-way ANOVAs, and they C and K are interchangeable in that case.
Okay. Got it. So, okay. I'll stop sharing. I'm going to try and calculate this real quick.
Okay. So that was the 15A number 4. Does anyone have any other questions on that one or any of the other section 8 questions? Kimberly, yes? I think you're muted.
Sorry, I was. I'm just looking at it right now, and it looks like everything on A is okay. Yes, yep. Now you just
so on yours was one of those rounding things. So you were looking at the repeated measure for the mean square, I got 26.6664 and you had 0.265. It was off in the decimal places. So when I did the sum of squared repeated measures, I got 80 exactly, and you got
79.9962. Yeah.
So I had to make sure the margin of error would allow for that difference. It was only allowing it to be different in the third decimal place, and I changed it to the second decimal place. So you were right. It was just that tolerance on the
round off error. Okay.
Yeah.
Yeah, that was a nightmare.
Yeah.
Okay. It looks like that item 1 is okay for me right now.
Okay, so anyone else have any questions with item 1? We good with item 1? Okay. Let's see. So item 2. Anyone have any questions on item 2? So that's 15B, number 3. So item 2.
So my question on this one was regarding the effect size being misleading. I wasn't quite sure how to answer.
Okay. Yeah, and this is part of the conversation we missed out on having Wednesday. So when you have repeated measures designs, you can calculate your effect size 2 different ways, and we call these the ordinary or the generalized eta squared, and then there's the partial eta squared. They both have the same number on top. It's what's on the bottom of that fraction that differs slightly. They both have the residual, but on the generalized, it's the total variance, all the other components. And for the partial, we exclude the subject by the subject to subject variance. And that makes it so that the partial eta squared is usually a bigger value. So on this particular item 2, when you do this problem, the general eta squared is what number?
0.094.
0.09. When you do the partial eta squared, it's
0.391.
0.39. And it's because you can think of it as a percentage, but it's out of a different total. So generalized 0.09, partial 0.39. The partial eta squared is going to be bigger. Now, the way that this can be misleading is that the partial eta squared is correct, that the way you interpret it is the generalized eta squared is the proportion of variance in the outcome accounted for by the repeated measure out of the total variance. The partial eta squared is the after accounting for subject to subject variability, then what portion of the variance is accounted for by the repeated measure. So it's after we already established that there's person to person differences. So the partial eta squared is after you're accounting for person to person differences. Now it can be misleading because what if somebody is going to go and they're going to try to do a similar experiment? Now this one was looking at different textbooks. And so we were not doing repeated on the same person, or wait, no. This is the audience, the blood pressure. So you have each participant came in and you have the blood pressure and you ask them to imagine that they're giving a talk to one person and their blood pressure is here. And then there's a washout period. So there's no carryover effect. Let their blood pressure come back down, distract them some way. Then imagine you're talking to 20 people, measure their blood pressure, and we have kind of a go back to normal, waiting, washout period. And then the third time, imagine that it's a large audience and measure the blood pressure. So each person has 3 blood pressures. Again here, because each person is measured 3 times, we can partition out or take out the person-to-person differences. Not everyone has the same blood pressure. If we're just sitting here right now, all 7 of us are going to have slightly different blood pressures because of different person-to-person differences. And if we want to acknowledge person-to-person differences, but we don't really want our study to be, like our statistics needs to acknowledge that there's person-to-person differences and to take that into consideration, but that's really not the focus. We don't really care that people are different. We want to control for person-to-person differences. So the partial eta squared does that. But what if somebody else was going to redo this study to try to replicate our results, and instead of having each person do all 3 scenarios, you divided your group of people in and did this third only do the one person scenario. This third of the people only do the small group, and this third only do the large sample. So we do it as an independent groups instead of as a repeated measures design. That's when we can have the eta squareds be misleading. So our partial eta squared of 0.39%, that only is going to translate to other repeated measure studies. If somebody is to repeat the study but do it as independent groups, their effect size is probably going to be closer to 0.09. And you're only going to see that large effect size of 0.39 if it's done as a repeated measures design. And so that's why it's very important that you say which eta squared you're doing, or even better, give both of them when you report your results. Generally, it's preferred to publish the partial eta squareds, but if you're doing a lit review and you're reading an article about, and you're going to be reading lots of articles, some of them are going to be done as repeated measures and some of them are going to be done as independent groups. Those two eta squareds don't mean the same thing, so you can't compare apples to oranges. So you need to make sure that you know, and hopefully the authors made it clear whether they're reporting a generalized ordinary eta squared or the partial eta squared that is after accounting for person-to-person differences in the repeated measures only scenario. That was a lot of talking. Laura, you're laughing at me. Hillary, did that make any sense whatsoever? Brian, we're talking about 15B, number 3, C, right? C. So the generalized eta squared will always be smaller because the partial eta squared is after accounting for subject to subject variability. And it also is subject to, it can be affected by violations to the assumptions of sphericity and homogeny variance and balance of groups. Okay, any other questions about that one? That's item 2, right? Okay, what about item 3? What do you notice in item 3? I had you do the same data as a match design, assuming sphericity, a match design, not assuming sphericity, but using the greenhouse geyser correction. And then the third time, which is actually number 5, you do it ignoring the matching. What stays the same?
The SS, the degrees of freedom stayed the same.
Yeah, the summa squared for book stays the same. The degrees of freedom does change if you do the greenhouse geyser.
That's true, it does.
But the big thing that changes is the residual. The thing that changes is the residual, especially when you do matching versus not matching independent groups. And so hopefully that shows to you or illustrates that it's more powerful if you can do matching, contingent on that you can actually match on things that matter.
Hey, Sarah, on part A, I don't have a check answer button.
Part A?
On that Anova on the data.
It goes away when you do the third check.
Oh, except for I didn't get it right. So I don't know what is going on.
Because I see that, does anyone else see the check on 4A or 5A?
4, number 4.
4A, I see it on mine. Does anyone else see the 4A, 15B, 4A have a check answer button? Yeah, I think it should be there.
Oh, it's not. I can show you my screen. I've refreshed it.
I believe it's not there, but I'm guessing it's because you used it 3 times.
No, it says.
No?
Oh yeah, I did. You're right. I used it 3 times. Okay, that's why. I'm sorry. You're so right.
I was like, I know you're not lying, but I can see it. Okay. All right.
I struggled, so that's why I didn't get it right.
Yeah.
So I guess I don't understand that.
I think if you refresh it, so that was one on 15B4. Melissa, right? This is one where we had to increase the tolerance. We had to increase the tolerance on some of these because of the rounding. And so let's go over it. So on part A, Kimberly, do you want to share your screen? Why don't you go ahead and share your screen?
Yes, I'm pulling up my
And
R.
I can tell you if it's right. It'll be scored according to how I fix the answer key, not how your check answer button told you.
And let's see, share screen. And it's probably sharing the wrong one. Let's see, is it sharing that one? Yes. Okay, good. Yeah, so I don't think I knew what I was doing here, so everyone don't.
Okay, so there we go. So yeah, so 76.75, 3 degrees of freedom, so it's 25.58. That's correct. And then for the residual, 27.5 degrees of freedom, 24, divide, you get 1.15. So again, it depends on where you rounded.
Mm-hmm.
And then the F value, the way I rounded it, I got 22.33, and you get 22.
Yeah.
So
I remember this. The R did 22.33, but when I did this by hand, I got 22.25.
Well, when I did it by hand, I kept 3 decimal places, and so the mean squares were 25.583 and 1.146. And so if you only rounded those to 2 decimal places, then you get 12.25. When I kept the mean squares at 3 decimal places, then I matched R. So
okay, so
it's just
so
rounding,
far,
and I increased.
This is just round off error.
That's just round off error.
Okay. Okay.
So, and then if you scroll down, let's look at the other ones, because I think that we had to do the same thing on the second one. So on this one, yeah, it's 22.35. That's correct. Yeah.
But, okay,
Yeah.
but I'm still getting it wrong though.
76.75. Can you push refresh on your browser?
Yeah. I don't know, maybe my residual was wrong or something?
Oh, it's taking its sweet time. Okay.
Okay, so
27.5, 16.16. Okay, that should be right. Can you check your answer?
yeah, it doesn't like these.
27.5, those should be right. Okay, let me go into mine. This is the second one, so this is part C. So it's marking, which one was it marking wrong?
The p-value and then the sum of squares residual.
Sum of squared residual, so that's box 6 on mine, and it should be,
It's saying it should be 640, so I don't know, did I not do it right?
That's, yeah, 640 is not right. It should,
okay. Okay, good.
It should be 27.5, right?
Well, I mean, I think so, but I'm.
And then the p-value, that's box 5, should be, oh, it's not, it doesn't have one in here. I swear it was in there just the last time I checked. Okay, let me see. Okay. Now, refresh your screen.
Okay, it'll take a minute.
Yeah, it will take it a second. Okay, let's go down. I think, do you have like one check left?
Yes.
Yeah. Okay. There we go. Okay, that's good.
Okay, so I can then share, elaborate.
And then wait, the next one we do it the 3rd time where we, yeah. Does this one got marked right?
This
one.
one.
Haven't checked it yet.
Yeah.
Okay. All right. Okay.
Okay.
Okay. Anyone else have any questions on that one? If you do, if yours was marked wrong, especially on, what was that, part C, make sure you refresh your screen now, because I've corrected those. You good? Okay. So that was kind of a long item. Okay, item number 4 is for 15B number 6. Questions on that one? Yes? Good? Questions? Anyone have questions?
It's taking a minute to load. Hang on. Okay, no, I'm okay on that one.
Anyone have any questions before we get to section C? No? Okay, good, good, good. Who has questions on section C? Okay, let's go over section C. So in section C, we have question number 1 and question number 3. So we'll do number 1 first. So this is where you're supposed to separately do men and first women and then men, looking at the anxiety over time. Okay. Questions right off the bat? Okay.
Yeah, what I got in my output didn't match. It's not making, I don't know if it's a round off error again, but like my output,
Okay.
I just.
Leah, do you want to share your R screen?
Sure. Let's see. I'll have to move this and then share and then our studio. Yeah, that one. Oh, I don't know why those pictures moved. Okay, so let's see.
Okay, so this is the, see, not the textbook one.
Is this the textbook question?
No, it's the C one.
Oh, sorry.
The anxiety at the 3 time points for men and women. If you go over to your
oh yeah,
side, the little C1, down a little bit more, C1, there you go. Okay, so yeah, so this is what I wanted to show you guys, because again, Melissa just asked this, so I knew I had the heads up that this was going to be a question for everyone, because it obviously wasn't good enough the way it was on the lectures. Okay, so on what we're looking at right now on the R code, this is done correctly. So it's got anxiety being modeled as tilde wave 1 for no independent groups, and then inside the parentheses, it's time is repeated on subject. So we have anxiety at different times per subject. And when you do summary of the name of the output, this gives you 3 basic chunks of output. The top chunk of the output gives you the results if you assume sphericity. So you'll notice the degrees of freedom. Now that intercept line we always ignore. So we want to look at the second line that says time. So the degrees of freedom are 2 and 112 with an F value of 4.03 and a P value of 0.020. If you put that in, it will be wrong because of the next section that comes after that. The middle chunk of your output is Munchley's test for sphericity. And when you look at the p-value on that test, that indicates that you have violations of sphericity, which means you should not do the top part. The top part was assuming sphericity. So instead of assuming sphericity, we have evidence sphericity is violated. So we need to look at the bottom part, which will show us different corrections, which are band-aids we can put over a violation of sphericity. So there's 2 main ones that get outputted. There's Greenhouse Geyser and the Hund Felt. We are gonna always use Greenhouse Geyser because that is like the accepted, most commonly used social science like one to use. But neither of them are always better than the other, but the Greenhouse Geyser is generally pretty good. Now I will tell you, I'm not a fan of this adjustment. If you're violating sphericity, and lots of statisticians will agree with me, you should not be doing an Anova method. Instead, you should use a multi-level model. But multi-level modeling or mixed effects modeling is a lot more complex of an analysis. And so people came out with this Greenhouse Geyser. In fact, Greenhouse and Geyser came up with this correction to kind of get away with doing an Anova when you really shouldn't be. So what you do is they have a formula that we don't even have to pay attention to that creates an epsilon, calculates an epsilon number. So that's the first one. Yeah, Kimberly, can you highlight it? That GGEPS, that's the Greenhouse Geyser epsilon number. And epsilon is like a curly E Greek letter. That number, the 0.846, that number you times both your degrees of freedom by. So your degrees of freedom are 2 and 112. Both of those degrees of freedom numbers need to be times by 0.846. Now your F value stays the same, but because you change your degrees of freedom, it will change the p-value. And sitting next to that epsilon number is what your new p-value will be. Now, Kimberly, if you'll go down on line 770 and add a new code chunk, there's kind of a quicker way to not have to multiply those numbers. Now just type the model name without the summary around it. So fit, ANCS, female. Now if you run that, oh, yeah, you haven't run everything above, so it's not gonna, oh, the data isn't even loaded. Yeah, up there, yeah. Oh, you don't have the packages loaded. So this happens a lot. So, you know, you probably have had this happen before. If this happens to you, you can hit, instead of the play button, the run all above, and it will, sometimes it takes a little time, but it'll go to the top and it'll run everything as if you'd been working on this before. So you don't have to, you can go right down to reading the data in. Yeah, that one. That one should run, yeah. If you ever get a message that it can't find the pipe, that's probably because you haven't loaded your packages yet. Okay. Yeah, so there's fitting the model. Summary gives you all three pieces: the assuming sphericity, Munchley's test of sphericity, and then the greenhouse geysers corrections. If you do just the model name, notice the degrees of freedom when you do just the model names. They've taken your epsilon, which is 0.846 this time, and times your degrees of freedom. 2 times 0.846 comes up to be 1.69. So the correct degrees of freedom are the decimal numbers 1.69 and 94.78. You'll notice the F value does not change. To do the greenhouse geyser epsilon correction, you only change the degrees of freedom by timesing both degrees of freedom numbers by that epsilon, whatever that formula says it should be, and that creates a different p-value. You'll notice the p-value here is the p-value that was shown in the bottom part of your summary output. Okay. Brian, that makes sense? So that's why it was marked wrong. It wasn't that you guys were doing anything wrong. It's when you do a repeated measure as Anova, you must look at the Munchley's test of sphericity to know whether or not you need that correction. So that's for females. So what do we say here? Does anxiety change over time for females? Yes, our p-value, even after the correction, is smaller than alpha 0.05. Our p-value is 0.027. So yes, females' anxiety levels are different at least one of the time points. Now, when you do it and then you can do the post-hoc test to see which time points. Now, Kimberly, can you go back up to that plot? Okay, so this was another thing that in office hours on Thursday, asked about it. So inside that EM means, this is one thing, when you do the EM means EMMIP, the EMMIP is, IP is for interaction plot. We don't have an interaction here, but it's still the command. It will only do the means. It always zeroes in on those means, and that looks like everything is like wildly different. But if you'll notice the y-axis, it's zoomed way in. So I prefer to add confidence intervals. So it's in the direction. So after you have the tilde wave time, put comma, capital C, capital I, little s equals true, and it will make confidence bands, and then it won't be zoomed in so much. Okay. If you look at the post-hoc tests, they tell you that baseline is different than pre, but pre and post are essentially the same. So when you write about this, you could say that after the announcement of the pop quiz, anxiety levels went up, and they remained high even after the quiz was finished for females. So the Anova said there's at least one time point that's different. The post-hoc pairwise tell us is an initial increase that remained high. Now for men, what do we see with men? Do we see the same thing?
There was no significance for
We
men.
see no significance. Now with the summary, we look at the top and it's not significant, but what happens when you look at Munchley's test? Munchley's test tells us we need to apply the epsilon correction. Let's do the greenhouse geyser. The easiest way to get those results is just to type the name of the model alone in a chunk, and it will do the multiplication for you. And it will give you those decimal degrees of freedom. And so those are the numbers that you need to enter in the assignment, because we should be using the epsilon correction here, not assuming sphericity, because Munchley's test showed us we have violations of sphericity. We have evidence of violations of sphericity. So when you do that, we still have non-significant results. With or without the epsilon correction, we have non-significant results. So do we need to do post hoc tests? We don't need post hoc tests because there is no evidence of any difference. So we don't need to see where the difference is, because we're saying there's basically no difference. For men, the anxiety levels were pretty much, there's no evidence that they changed at all across time. Now, in this analysis, we did female and then we did male. Today, we're going to learn how to do them both simultaneously, looking at time as a repeated measures factor and gender as an independent groups factor in the same analysis. At this point, we've only done independent factors, independent groups, or we've done repeated measures. Today, we're going to do mixed ANOVAs, which use both repeated measures and independent groups at the same time. That's the only difference today. Okay, so we don't even need a means plot because there is no difference. Okay, so C, how's C?
I didn't get that one right either. I don't know what I did.
Were you not right because of the T value? Because their answer key was wrong for the T value. I had 0.02 instead of 0.20 for the T value.
Yep, that solved it. Good. We're okay then. Thank you.
Okay, so what do you notice about a repeated measures ANOVA and a paired samples match pairs t-test?
Well, you should get the same p-value.
You'll get identical p-values, and the t number squared will equal the f value.
Yeah.
And the denominator degrees of freedom on the ANOVA are the degrees of freedom for the t-test, and the repeated measures ANOVA will always be 1 for the numerator degrees of freedom if you have 2 groups. Any general questions, things you want to talk about with the repeated measures ANOVA or ANOVAs in general, because we're going to take it a step further today. And so if there's any like hiccups, let's get these worked out now. Let me know, please. Why would we use an ANOVA? What's a situation we want to use an ANOVA in?
We want to look at the interaction with more than one variable.
We can look at interactions between more than one variable. Yep. What kind of variables can we investigate? What kind of dependent variable do we need to have? What kind of independent variables do we need?
They're categorical variables, right?
Dependent or independent?
Are independent or categorical? Dependent.
Our independent variables have to be categorical, mutually exclusive. We can have 1 independent groups or 2 independent groups. We can have 1 repeated measure, and today you could also do 2 repeated measures. That's usually called a panel design. You can also have 1 of each or 2 of each. That's mixed design. So our independent variables, our predictor variables, have to be categorical. What about our dependent variable?
Wouldn't the dependent variable need to be like numerical or ordinal in order to?
Hopefully a little more than ordinal. Hopefully it's
Continuous.
interval ratio continuous.
Continuous, yeah, sorry.
Yeah. And what are the assumptions that keep coming up with all these kinds of ANOVAs? What do we need to have?
Homogeny of variance.
Homogeny of variance.
Normal distribution.
Normal distribution within each group or subgroup combination.
Independent groups.
Independent groups if it's an independent grouping variable.
And then now sphericity.
And now sphericity for repeated measures. Yeah. ANOVAs can look at a lot of different things, but they are restrictive in their assumptions. Today I'm working on looking at a study that was done here at Utah State, and we have typical developing and autistic children. What kind of independent variable is that? Independent groups or repeated measures?
Independent groups.
Independent groups, because the child was either typical developing or autism spectrum disorder. They were one or the other, so that's an independent grouping variable. But then they had each child read 4 passages. And they were like paragraphs, like mini stories, and they looked at how many words they read per minute. And randomly, one passage was in a silent room, one passage was in a room with some white noise, one was with a single talker recording playing, and another one was with classroom babble playing in the background. So they had 4 passages, one in a different, each passage that they read was in a different noise condition. Is noise an independent grouping factor or a repeated measure?
Repeated measure.
It's a repeated measure because every child read a passage under all 4 of the conditions. So we had a repeated measure, but they also were each child was in one of 2 independent groups. That becomes a mixed design. We say mixed because we are mixing independent groups and repeated measures. So how many combinations are there? 8. But each child only had 4, but the typical developing child, we have 4 averages, and the autistic children, we have 4 different averages. So we have 4 values per child, but the children fall into one of 2 groups. So that could be done with a mixed design ANOVA. That's not the analysis that we're going to do for this publication, and the reason is we want to control for child age, because we had children from 1st to 8th grade in this study, and our outcome was how many words per minute they read. That's our continuous interval ratio scale that we're comparing the averages of. And how fast a child reads, the correct words per minute, is very different based on the age. So we wanted to control for age. Age is a continuous variable in this case because we have how many months old the children are, so we could convert it to decimal years. You can't have a continuous predictor in ANOVA. There is something called ANCOVA that you might have heard. It's analysis of covariance, which kind of allows you to have one continuous variable, but it doesn't let that continuous variable moderate a relationship or have an interaction with any of the factors. So ANOVA is very limited in how you can add a covariate. So we moved to a multi-level or a mixed effects model, because then we can have continuous covariates. We have age, we have the child's IQ, we have their hyperactivity Connors score, and we have a bunch of other scores that we want to control for and allow moderation effects. And so ANOVA was too restrictive. Also, we violated homogeny of variance and sphericity quite radically. And so ANOVA is very flexible in as long as you only have categorical predictors or independent variables. You can have repeated measures and you can have independent groups, but they have to be categorical. So I want you guys to know this, what the method can do as well as what it cannot do. Now, even though I know that you're rarely going to use ANOVA method as the only technique you're going to use for anything you do, the things that we learn about are going to stick with you for all the other models you will ever look at. The idea of having effect sizes, significant p-values, interactions, all of these things will continue on. So that's why we call this class statistical foundations. Those foundation ideas are more important to me than just Anova, teaching you Anova. Okay. Are you ready to get into mixed design? Okay, I'm going to go ahead and share my screen. All right, so I need to bring up the PowerPoint. Bring it over to this. Okay, so this slideshow is pretty short. There's only 10 slides. Woohoo! Right? Okay, so let's see if I do this. Oh, no, that's going to do, I have to choose, let's see, slideshow, no, view. No, it did it again. I did this the other day. Does anyone know how you,
Trying to do presentation mode?
I'm trying to switch monitors. There we go. I got my monitor switched. There. I want to have that monitor here. So I can see you guys. Okay. And then I still want to have this one over here. Okay. There. Okay. So these are sometimes called two-way mixed design. But they're, before when we did chapter, what was it, 13 or 14, we did two-way ANOVAs, but in that case, both variables were independent groups. Mixed design specifically means we have at least one repeated measure and at least one independent grouping factor. We're mixing the two together. Okay, so here is an example scenario of when this would be an appropriate technique. So Dr. Professor is interested in determining whether the average man wants to express his worries, oh, we've heard this one before, right? Express his worries to his wife more or less the longer they're married. However, it may depend on the age at which the man was when he got married. So not only are we going to measure this expression scale repeatedly at 1 year, 5 year, 10 years of marriage, but we're also going to split our men into those that were married when they were older, middle age, and younger. Now it's important here, we can only use categorical independent variables. So age, we have to categorize it. And I'm going to stop here because if you have a continuous variable, should you split it up into just younger, middle age, and older? Please think very carefully before you do this. Anytime if you have a continuous measurement, you know how old these people are when they get married, 21, 37, 52, you have that actual number, and instead you choose to divide it into younger, middle, and older age, you are going to be throwing away information. And that is usually a bad thing to do. Here we're going to do it because hopefully there is a meaningful developmental or theoretical reason why that we would choose these ages to break it down. And two, we're doing it just to illustrate an ANOVA method. Now there are some times when we only have categorical variables that only can be defined categorically. Sometimes I've worked with depression scales, and we had a depression scale that actually calculated a number between 0 and 40, but really it's like, what's the difference between a depression score of 26 and 27? It's kind of not that accurate, but we do have clinically significant cut points where if you're below 8, you're not depressed. 8 to 20 is considered mild depression, and 20 to 40 is clinically significant depression. Where there's clinical cutoffs, that's a time where it would be appropriate to collapse into maybe none, some, or high, or young, middle, and old, or some categorization. But I would always caution against that in the real world. But in this example, we do that. So what is the repeated measure in this case?
Is it married time?
Marital time. And how many levels of the married time variable are there?
I think there's 3.
Year 1, year 5, year 10. Oh, and baseline. So when they first get married. So there's actually 4 levels at baseline, 1 year, 5 year, and 10 years later. 4 time points, 4 levels to the married time factor. What's the between subjects factor? Now remember, between subject factor is another name for independent groups, where someone belongs to one, the other, but only one group. What's the between subjects factor?
Isn't
Kelly,
that
I see you
the
mounting.
age?
Marital age. And how many factor levels are there? 3. We've chosen to go with young, middle age, and older age. There are 3 levels to our between subjects factor. And what's the outcome here?
They express their worry.
The expression scale score. However, there's probably a lot of questions they ask and then they add them up or average their points or something like that. Okay. Here's another situation. And this is going to sound familiar. So Dr. Test wishes to compare reaction times differences for 3 subtests of the Stroop test. So subtests of a whole test can be looked at as repeated measures. So he's looking at Parkinson patients, and the 3 subtests are called color, word, and color word. Dr. Test believes that any differences may be influenced by the sex of the individual. So we need to decide what's the repeated measure or within subjects factor, how many levels does it have? What's the between subject or independent grouping factor, and how many levels does that have? And what's our outcome variable? So let's start with the first one. What's the repeated measure factor?
3 test types.
The test type, of which there are 3 levels. What's the between subjects factor?
The sex of it? Oh, no.
What, Kelly?
I started to say the sex of the individual, but,
Yes,
okay.
it is, because they belong to one or the other sex. Do we know how many levels of sex they're going to use? We don't. They're probably going to do male and female for Parkinson's disease patients, but they could have a 3rd or a 4th or a 5th level, however you're going to define sex. Usually we're going to go male and female, but if you want to do male, female, and then transgender male, whatever you're going to do with that. I'm not here to tell you what to do. What's the outcome variable?
Reaction time differences?
Reaction time, and it's going to have to be measured maybe in milliseconds or seconds or minutes or however, but it's going to be a continuous interval reaction time. Okay, can you see how we're like bringing together 2 aspects of ANOVA we've already done? We have our between subjects and our within subjects, just putting them together. So the way this would look in real life, you're going to usually have a sample of people, and the people are going to be in different groups. Now we can either randomize into the groups, or the groups could be already self-selected or already pre-existing. So sex is going to be a pre-existing group, right? It's not one that you randomize. It's an observational grouping factor, but that can still be a grouping factor or between subjects factor. You can also randomize those into different groups and do different things. So it can either be experimental grouping or observational grouping that you have the participants in. That's just like our one-way ANOVA, that we have the independent groups. But then each person within the group is going to get either multiple time points or multiple replicates, just like our one-way repeated measures ANOVA. So within group 1, so that would be like the male, they'd have time 1, 2, and 3. That's baseline 1 year after they got married, 5 years after they got married, 10 years. And then in group 2, that would be like got married when they were middle-aged, then they'd have their repeats. So we have both things going on. So when there is a repeated measure for one of the factors, but not the other. So we have 1 repeated measures factor, 1 independent groups factor. 1 of each predictors. So the between subject factors can also be called the independent grouping factor. Participants belong to only one group, only one, they can only have one level of the factor. That's the between subjects factor. They can only have one, mutually exclusive. The within subjects factor, that's also called a repeated measure, and all participants should have all levels. So here's another drawback to ANOVA. In ANOVA, if you have a repeated subjects factor, whether that is time points or like 3 subtests, if someone is missing one of the repeats, they cannot be used at all in repeated measures or mixed design ANOVA. So this is a big deal if you're doing a longitudinal study. What about that the men expressing their worry or whatever, expressing to their wife, married at baseline, married 1 year, married 5 year, married 10 year. You can only use people that have all 4 of those time points. 10 years, what's gonna happen to your sample over 10 years? Repeated measure and mixed design ANOVA, you have to have complete data on a person. That's a caveat to the method. Now, I will tell you this to, like, if you are missing some data on some person, maybe you have a baseline in 1 year, and maybe you missed 5 years because you couldn't find them, and then they're back at 10 years, you cannot use them for a repeated or mixed design ANOVA. You can use their data for a multi-level or a mixed effects model. So that's a bonus, another bonus to doing not an ANOVA. ANOVA is very restrictive. You have to have complete data. All participants have to have all the repeats. If you're doing the Stroop test and you have color, word, and color word, you have to have all 3 subscores. If they had a problem with one of the subtests, you cannot use them in your analysis, even if you have 2 of the 3, if you're doing an ANOVA method. Okay, so down here at the bottom of the slide, I've thrown up the formula. Usually when we write our formula, we put the continuous variable first, tilde wave, and then first comes the grouping variable name, and then inside the parentheses is the repeated measure name. Now before, we only had one of those 2. We either had the grouping variable outside the parentheses or the repeated measure inside the parentheses. What did we put in place of the one that we didn't have? We put the number 1. When we were doing the independent groups variable, we had the 1 inside the parentheses. And when we did repeated measures ANOVA, we had the 1 outside the parentheses. This time we're not going to have any 1s. We're going to have both variable names in our model, because we're going to have both an independent grouping and a within subjects factor repeated measure. Both of them. Yeah, but guess what? There's no new syntax. Okay, so when we did the simple repeated measures in ANOVA, we had to know whether there was a general pattern across time. That's like the idea of sphericity. With a mixed design, we have to have that general pattern across time, and subject to subject differences are only due to the independent group. When we did simple repeated measures design, we ignored subject to subject variability. We assumed that it was just error. Here, we're going to say some of the subject to subject variability is due to their sex, which group of sex they fall into, or which age group at married they fall into. So analyzing the within subject variable, we already saw that we could calculate an F ratio for the main effect of the repeated measure. And now we can take that F ratio and we're going to recalculate it to take into account the difference, but the subjects separated into their subgroups. The top number for the repeated measure is not going to change. It's the denominator that's going to change. Our within number is going to change for our repeated measure factor. So most of the subject to subject variability, we're going to have subject by repeated measure interaction. A lot of that's going to be due to the group by condition interaction. So we're going to remove that out. I think it's better to look at the degree of freedom tree breakdown in a second. I think it's the slide after this next one. This next one's the assumptions. So these assumptions are going to be a combination of the assumptions we've already seen before, right? So independence. We have independence between subjects that are lost someone. I want to put this out here so I can make sure to find who did we leave, who left, who did we lose. We lost someone. Did we lose someone? 1, 2. No, we got everyone. Okay. My fault. I was counting. Okay. So we are going to assume subjects are independent of each other, the people. And then this is another very restrictive assumption. We're going to assume equal spacing of the repeated measures if they're in time. So this was one that hopefully you got last chapter, that when you have a repeated measure, Anova assumes that the repeated measures are equally spaced in time. Now, on our husbands being married, expressing themselves, what were our times? Baseline, 1 year, 5 year, 10 year. Baseline, 1 year, 5 year, 10 year. Are those equally spaced in time? No. So Anova really doesn't model it correctly, because baseline to 1 year, that's a 1 year gap. 1 year to 5 year, that's a 4 year gap. 5 years to 10 years, that's a 5 year gap. So the gaps are not equal. The mixed Anova, or even a repeated measure Anova, assumes that they treats them as if they are equally spaced, which is usually a stretch. We have normality assumption that the outcome, the dependent variable, for each time point or each repeat for each group is normally distributed. Are these looking familiar? Yeah. Homogeny variance, that the outcome has the same variance, the same spread for each group at each time or each repeat. So if I'm doing the Stroop test for men and women, I'm going to assume I have the same spread for men for color, men for word, men for color word, female for word, female for color word. All 6 of those sub piles of scores have to have the same spread. Sphericity is still an assumption. So we take all the assumptions for independent group Anova and all the assumptions for repeated measure Anova, we have them all together at once. So we're assuming sphericity, homogeny variance, normality, equally spacing, and independence. All of those assumptions. What's the likelihood you're going to meet all those assumptions with observational data? Highly unlikely. And having complete cases all over the place. Yeah. But the things that we're learning are not a waste of time because they apply to other methods too. So sometimes we have data like this, sometimes we don't. Okay. Yeah, so there's the major thing. You have to have complete cases. So we saw the degrees of freedom tree. This is right straight off of our formula sheet. When we did a one-way Anova back in chapter 12, we took the total degrees of freedom and the total sum squared, and we divided them into 2 piles, between subjects, between groups, and within groups. Very simple, just one partition. When we did two-way factors, we did further into the 2 variables and their interaction. When we did repeated measure, we did between subjects and within subjects was due to repeated measure and the subject by repeated measure interaction. Now we're going to combine all this together. You ready? Gag, right? So we're going to start with our degrees of freedom tree splits the same way of our sum of squares does. We're going to start with the total and divide it into between subjects, within subject. That first branch looks like our repeated measures tree. Divide it the first branching. Between subjects, now we're going to further divide what's due to groups and what's within group. So we're going to start with a repeated measure, and we're going to split the between subject like we did before, between groups and within groups. Now I've got grayed out boxes here. The grayed out boxes are the denominators. So if we look at the one-way Anova, how many F tests did we have in a one-way Anova? We had 1 F test. It was the groups, and what was the denominator? Within groups. The gray box is the denominator. When we did a two-way Anova, we did rows, columns, and their interactions. Those were the 3 numerators. And what was the denominator? The within cell, this gray box. When we did repeated measures ANOVA, we could look at, we usually only test the repeated measures factor. And what's its denominator? The subject by repeated measure interaction. Subject to subject variability is just set aside, it's controlled for. Now we're going to divide that subject to subject variability into explained and unexplained. We're going to have two different denominators now. Now, before we move on from this slide, let's look at our eta squareds. For a one-way, how many different eta squareds do we have for a one-way ANOVA? We just have one eta squared. For a two-way ANOVA, we have ordinary, or the generalized, and we have the partial. For a one-way repeated measures ANOVA, you can have them both as well. I only have one listed here. Which one's listed here? Is this the overall, ordinary, generalized, or is it the partial? I'll give you a hint. What's in the bottom? Is the bottom the total sum of squared, or is it just part? And the denominator is just part. What part is left out of the denominator? We've got repeated measure, subject by repeated measure. What's left out of this denominator? The part that's between subjects. So this is a partial eta squared. Look at all the different eta squareds that we can make for a mixed design ANOVA. Does that make your head spin? Yeah, I'm going to show you which ones. When you're doing a repeated measure, you're always going to do a partial, but you need to make sure you put the little p on subscript on the eta squared so that the people reading it know you did a partial. We almost never are going to do a generalized. Yeah, we'll come back to these. Oh, that was the last slide. Maybe we should put it here. Well, the group variable, usually we do the repeated measure and the group variable. There are two different formulas for the group variable, and it depends on if you assigned the grouping variable or you observed the grouping variable. Which one would I use, assigned or observed, if my variable was sex? My between subjects factor was sex. Which one would I use?
Observed.
Observed. What if it was whether the room was light or dark? Probably going to be assigned, because unless we let people choose which room they go into, probably going to be assigned. Okay. All right, that's all the slides. Anyone have any questions about reading the chapter? Should we pull up the discussion board? Pull up the discussion board. Let's see, mixed design and over. Oh, Leah loves R. I love R too. Yeah, usually the between groups factor is usually observed. It's not usually experimental, but repeated measures factor usually is randomized. Okay. You guys jump in with any questions. I'm just scanning over this to see if there's something that we need to hit. Oh, confused where to get the different pieces to do the eta squareds. Yes, yes. Okay, we'll do that. And sphericity. We talked a little bit about it, but we'll do more. Okay. Yes, Brian, you're right. We generally don't have the same number of subjects per group a lot of times. So that's when you want to move to a multi-level type analysis, a mixed effects. Okay. All right, so someone was saying, where do we get these SS's from to put in these eta squared formulas? All right, this is what we want to know. Okay, we get them from R. Should we start in the homework and see if we can find them? Let's start in the homework.
Hey, could we take a quick break?
Thank you. Let's do, we're doing good on time. Let's do 10 minutes. Shall we do 10 minutes and come back at 10:02? Let's definitely do that. 10 minutes at 10:02. I can't find it. It's frustrating. Let's see.
Sarah, are we going to be going over the hand calculations or the R for homework 16?
We could probably do both.
Okay, I was just curious which one I should
Yes.
pull up. Okay.
Okay. I found it. Okay. Um, wow. I'm going to put this in here, and I'm going to put it in here, and I'm going to actually put that in here too. Did it not go in here? This is due. No. Did it go into here? No, it went into here. Right there. Okay. I'm gonna put that there, and I'm going to link it here.
Sarah, before we get started,
Yes.
did I miss something before class started about the next test?
No, you did not miss it. We need to talk about it.
Okay. I'm like, might want to know if it's going to happen Tuesday or what today or what I need to do to panic.
Yeah. Number one, don't panic. Number two, let me see here. Let me open this up and see if it's ready to go. I don't want to show you guys the quiz, obviously, before you take it. Let's see. Okay, the test is ready to go. It has 2 multiple choice questions and 1 situation where I give you all the code and output and ask a couple questions about it. How's that? Now, I heard not a lot, but a little feedback on the last test that how did the last test go lengthwise?
It still took me an hour, even though you said it would take 20 minutes.
An
It took me a
hour?
long time to write the.
An hour?
It
It's
took
the
me a long
APA
time.
that takes forever.
Yeah, it took me about an hour too.
Okay,
think
I'll
it's
tell you what.
about-
Here's the good news. This next test, I just checked, the APA is already written for you, but there are mistakes in it that you must fix. So you copy and paste it and fix the mistakes. Should that speed things up?
Wait, but we
It
can't
won't let you copy in Panopto.
Huh?
It won't let you copy in Panopto. But I mean,
Oh,
like,
but it is shown above. So you just, so it's already typed out with mistakes in it. So then you retype it, fixing the mistakes.
that's better than coming up with it on our own. Yeah.
Is that better? Okay. So it's all ready for you to take.
Awesome.
And which chapters again? 15 and 16, or is it
15 and 16. And 15 is just repeated measures, and 16 is mixed design, which is repeated measures with an independent groupings factor thrown into.
And then Wednesday, we're going to go over the last 2 chapters.
In the last 2 chapters, and I am going to send you an announcement that tells you what to focus on in the last 2 chapters, because we're skipping chapters 17 and 18. They're on, I think, I don't have the book right here. I think it's on like more regression, multiple regression, which you're going to do in 7610. So we're skipping those for in this book. Chapter 19 is about the binomial distribution. We're just barely going to do a little bit of what is in that chapter. And then chapter 20 has chi-squared tests, goodness of fit, test for independence, and let's see, equally likely, goodness of fit, and test of independence. So the first 2 are versions of the same thing. So they're one-way and two-way chi-squared tests. They are, students in the last 6 years, every semester have said they felt easier than the Anovas. How's that?
And Sarah, will you be holding office hours on Thursday, even though we don't have class?
Yes.
Okay.
I will be holding office hours tomorrow. I've already been requested to do office hours after class today. If anyone still wants to do that, I can do that. I can have office hours tomorrow evening and Thursday evening as well.
Okay.
Okay. So hopefully I have an article that I want to go over that I have put on the homework before, and it's not on the homework right now, but I want to talk about it because I think this is the pinnacle of this class, Mixed Anova. It's adding everything together that we've done thus far, right? And this article is actually a really good example of a ton of stuff. So I want to go over this. We can either do this first before the homework, or we can do the homework first and then do this the last. Think maybe a half hour. It's 3 o'clock right now. We go to 4:15, so we have an hour and 15 minutes. So if we do this for a half hour, that leaves us, what, 45 minutes for the homework? Which one do you guys want to do first? Article or homework first?
Homework.
Homework? Okay. Let's do homework
Sarah?
first. Yeah.
Just so I'm real clear, so the test is due by, and the homework for 15 and 16 are due when?
What does it say? Let me open Canvas here. Let me close the test first before I bring it over there.
Aren't they all due Wednesday at midnight for the first?
Right now, it says that they are due 17th, which is Wednesday at midnight. Yeah.
And our reading and discussion posts are due Wednesday at 10:30.
Let's see what it says on here. I know I changed them at one point, and I don't remember what it. Friday is when 1920 are due, and I'm going to actually delete 19. How's that? Because we're only going to do just a little bit. In fact, if you don't want to, let's see, where can I just delete? Where's just delete?
There it is.
Okay. Okay, so syllabus. Okay, so 15, everyone should be mostly done because we just went over it, right? 16, we're going to have 45 minutes to go over right now. So that should be mostly done by the end of today, right? And so that you have to finish up those 2 and do exam 5 by Wednesday. That gives you 2 days. And then by Friday, read chapter 20 and do its discussion points. And then homework 19 just has a couple on it, I believe. It's really short. I don't have it in here, that's right. And then 20 is the chi-squared test. This practice quiz, this was just, I don't know what that is. It's not.
Oh, that's Panopto's practice quiz.
That's right, to figure out how to use Panopto.
Yep.
So the
Doable.
exam 6 and 19 and 20 homework are all due Sunday night.
So that I can get your grades in Monday.
Okay, great.
Okay. And this exam, the APA is written, albeit with mistakes. You just have to rewrite it, retype it out, fixing the mistakes. So you don't have to come up with language on your own. 2 multiple choice, and then 1 example, output, situation, and you fix that. There's like 2 questions about it too. Maybe there's something about assumptions. I wouldn't be surprised. Okay. Okay, so we're gonna go over the homework 16 right now, right? Okay, so we wanna go over hand calculations first, and then R. Okay. There is some, not a lot, but a little bit of hand calculating. Oh wait, is it? Yes, there is, okay. And then we're gonna do my favorite example article the last half hour. And this favorite example article, I just barely, while we were talking, put a link to it on our homepage. It's Do Positive Psychological Exercises Work? A Replication of Seligman et al. 2005. This is what we're gonna go over. So this is a link to the PDF, last half hour. So 45 minutes. Keep on task so I don't get distracted. Stats is just so exciting, it gets me distracted. Okay. Okay. All right. Oh, I didn't delete this part. Oh well. No. A researcher tested 2 groups of subjects, 6 alcohol abusers and 6 moderate social drinkers on a reaction time task. What is drinking? An independent, between subjects factor, or repeated within subjects factor? Did I say that right? Alcohol abusers. We've got 6 alcohol abusers and 6 moderate social drinkers. Is that an between subjects independent factor or repeated measures within subject factor?
Independent.
Independent factor, it's the grouping.
Independent factor, it's a between subjects factor. Between subjects are between one or the other. So that's our grouping variable. Each subject is measured twice before and after drinking 4 ounces of vodka. What is our repeated measure?
Is it the 2? It's the 2 times that they.
It's the 2 times. Time is our repeated factor. It's either before or after the drinking of this 4 ounces of alcohol, of vodka, excuse me, specifically vodka. So it's a mixed design Anova because we have both 2 independent groups and this before and after repeated time points. So we can make some software and some books teach it as one Anova table, but it can be split into 2 separate Anova tables. So this Anova table is split, the between subjects factor and the within subjects factor, and it has the sum of squareds in it. We need to fill out the rest. So let's start with the degrees of freedom.
Hey, Sarah, can you let Laura in?
Oh, thank you.
Yeah.
Before I thought someone was missing and they weren't, now someone was missing and I missed it. Welcome back, Laura. Okay. So, groups. How many groups do we have? 2. So what's the degrees of freedom for group? 1. Okay, we'll fill that one out. Repeated measure is time. How many time points do we have? 2. So what's its degree of freedom? 1. Okay. Oh, we don't have our degree of freedom tree here. Those are the easier parts. Now, for groups, our residual is subject by groups. How many subjects do we have?
12.
How many? 12. Yep. So we're going to do 12 minus 1 and groups minus 1. So 12 minus 1.
Where did we come up with the 12?
No. Sorry.
It should be 8, isn't it?
6 and 6. Ooh. How many subjects per group?
Oh, 12. Gotcha.
We need our degrees of freedom tree. Where's our degrees of freedom tree? Here we go. I'm going to snip this out, a copy of this out. Okay. And, oh, I can't type. Oh, I can't type on there. Okay, let's see. What's our number of subjects? Is that
12.
6? But we have 6 subjects per
Per group.
group at, and we have 2 levels. So how many total scores do we have?
Just 6 for.
6 people for each group, so 12 people total, and we have a before and after score for each of our 12 people. So how many total scores do we end up with? The alcohol levels.
12.
We have
24.
24. NT is the total number of outcomes we have. So what are we measuring these? It doesn't say if we're doing their, does it tell? 2 groups of people before and after. It doesn't tell us what our outcome is. We might be measuring their blood alcohol content. We might be looking at their reaction time. We have some score that we're comparing before and after. And we have 6 people in each group of 2 groups of 6 measured twice for a total of 24. So that let's start at the top of our tree and fill it all out. So the total degrees of freedom is the total sample size minus 1. Total sample size, we have 24 scores, so the total degrees of freedom are 23. So let's do our breakdown. So between subjects should be n times k. N is 6 subjects for each of k equals 2 groups. So n times k is
12.
12 minus 1 is 11. Now over here, the within subjects branch, we should have nk times c minus 1. C is the number of levels. How many levels do we have in the repeated measure? 2 times minus 1 is?
1.
So 2 minus 1, this is 1. So what's n times k? N times k is 12. Do the branches add up? 11 and 12. Did they add up to 23? Good deal. Okay. Now let's go to the grouping branch. How many groups do we have? K equals 2. So this ends up being 1 degree of freedom. Now we've got a branch, right? So even before I do this like formula in here, how many degrees of freedom have to be in this gray box? If we have 1 here, how many have to be here?
10.
10, because we have to have it add up. So let's see, what's K? K is 2 groups, so it's 2, and then times n minus 1. What's n? 6, so it's 2 times 5 is 10. Okay. So when we do this side of our tree, this is our between subject branch. So when we do our F statistic, our numerator degrees of freedom are 1, our denominator degrees of freedom are 10. So if we come back to Canvas, it's 1 and 10. Now for our within subjects factor, we've got 3 things. We're gonna have 2 F statistics, 1 for the repeated measure, 1 for the interaction group by repeated measure, and then we have this residual, which is subject by repeated measure. So let's go back to our little tree. Where's our tree? Here. Okay, so repeated measure. Can I change my color? Let's go blue. The repeated measure. How many degrees of freedom do we have here? It's C minus 1. C is the number of repeated measures. 2 minus 1 is 1 degree of freedom here. Okay, we figured that one out. Okay, Now let's go to the middle white box. It's going to be k minus 1. What's k? 2 groups, so 2 minus 1 is 1. Now c minus 1, what's c? 2 repeats. 2 minus 1 is 1. 1 times 1 is 1. Okay, now it's the gray box all the way to the far right. K times c minus 1 times n minus 1. What's k? Number of groups, 2. And we have c minus 1, that's number of repeats minus 1. So times 1 times, the last part is n minus 1. N is the number per group, which is 6. Take away 1 is 5, so that ends up being 10. Did this branch add up? 10 and 1 and 1. Did it add up? Yeah. 1 and 10. Okay. The degrees of freedom tree I always refer to. That's why I put it on your sheet. But what are we going to do in the real world? Let R do it. But we want to know how R is getting the numbers. Okay. So we were given the sum of squared. We just figured out the degrees of freedom. How do we get the next column, the mean sum of squareds?
You just divide
Divide. So this
SS
first
by
box,
degrees of freedom.
SS by degrees of freedom. So 88 divided by 1. I like this math. Next one. 1380 divided by 10. 138. I like this math. And how do we calculate our F statistic?
Divide.
Divide what by what? What goes on the top? 88. What goes on the bottom? 138. Got it, Laura? Your eyebrows are saying what? Always for an F statistic, it's mean squared divided by mean squared.
Is it 0.6376? 0.6377?
Let's do the 3 decimal places.
Okay.
Oh, maybe 2 decimal places?
0.638?
0.64?
Oh. So do 2?
2 decimal places, yeah. 2 decimal places, it's p-values, we do 3.
Right. Okay.
Okay. All right. Is that going to be statistically significant? Probably not, because it's going to have to be bigger than 1 for sure.
Yeah.
Okay, so let's look at time. For time, what's my mean squared?
550.
550, we like this math, right?
Mhm.
For the interaction group by repeated measure, it's going to be
2.0.
2. Okay, I don't know if I've done my margin of error here, so we're going to check it here. So what about the residual here? Subject by repeated measure.
13.4.
Okay, we like these numbers. Okay, now the F statistic's a little more complicated. We're going to have 2 F statistics. They're going to have different top numbers, but they're both going to have the same bottom number. And both of them are going to have the bottom number 13.4. We can do this together. What's our first F statistic for the repeated measure of time before and after drinking the vodka?
I got 41.04.
I got that too. Anyone get, what about the interaction between the grouping variable?
0.15.
0.15?
Mhm.
Yes. Okay. So what critical value are we going to compare all of our F values to? All 3 of our F values have what numerator degree of freedom? 1. All 3 of these happen to have the same denominator degrees of freedom. What's the denominator degrees of freedom on all of these?
10.
10. So we're going to look that up in our F table for 0.05. Anyone have a handy F table? Ah, the textbook, yes. Appendix B? The B?
So 4.96.
I got that. So what are significant? Is the grouping variable significant as a main effect?
No.
No. Is the repeated measure of time significant?
Yes.
Yeah, because this F value is 41.04, Leah, so that's a lot bigger than our critical value of almost 5. What about the interaction between group and repeated measure? Not even close. So in this example, so what's the only thing that's significant is the repeated measure. So our outcome differs between before and after they drink the vodka, but it's the same whether or not they're an alcoholic or a moderate social drinker. Okay. All right, so here we have numbers of how many ounces of popcorn was consumed by each subject while viewing 2 emotion-evoking films. One evokes happiness and the other movie evokes fear. So we got a horror movie and a chick flick or something like that, I don't know. And so we have half of the subjects were assigned to eat a meal right before they watched the films, preloading condition, whereas the others did not eat before the film. So that's the no load condition. Okay, let me ask you, if we were going to do this, what is the repeated measure factor? And how many levels? 2, I see 2 fingers, Laura. What's the repeated measure with 2 levels?
Wait 1 second.
Yeah.
Is it the preload and no load?
Those are separate. Those are independent groups.
Those are
Yeah, they
independent
are.
groups. There are 2 independent groups. Half of the subjects were assigned to eat before, half were not allowed to eat before. That's the independent groups, the between subjects factor. What's the within subjects factor, the repeated measure?
The happiness and fear.
The 2 movies. Every subject watched both movies, the happy movie and the scary movie. So the repeated measure factor here is the movie or the type of movie. And there's 2 types, the happy and the scary. Okay, so how many subjects were in each group?
4.
4. There's 4 that ate before and 4 that did not, for a total of 8 subjects, and they each had 2 movies they watched. So they ate popcorn for the happy movie and popcorn for the scary. So how many different outcome, what's our N with the T total? 16. Okay, so we're supposed to, or this gets plotted in R. If we pull up our R. Let's see. Let's go to our R, not the key. Want to go to the skeleton. Okay. So whoa, is this what yours look like? Do you guys have this? Let me download what you guys have so that, do you guys have it?
Mm-hmm.
Oh, it's not showing up here. not showing up there. That's weird. Okay.
What number is it in?
Chapter 16, our skeleton. That's the PDF. 16. That's the log. No, I don't want that one. I want to have exactly the same thing on my screen that you guys have. So 16 skeleton. That one.
No, the one that we've got is the one that has 2020 spring on it. It's
Does
that
yours
other.
have the 2020 spring on it?
Mhm.
Let me see. I think I updated it. Okay. Let me. Let me change it for you. I know I updated it and I don't know if it's something important. So let me go into here and let me change it.
I don't know if this makes a difference, but there's no like section A.
Yeah,
That's what the questions are coming from.
kind of. That's what, yeah. So it is in this other one that I'm doing.
Okay.
So let me go to assignments. Chapter 16. Yeah. So edit assignment here. So this one, file, let me get this new one. It doesn't say spring. Chapter 16. So this one, it's this one. Okay, now let me push save. Save. Okay, now if you guys go to where it has the RMD, if you re-download this, it will not say spring of 2019 or whatever, and it will have the syntax to make this plot. Should.
So refresh first and then download.
Refresh first.
Okay.
Is this the right one? Oh.
This looks like what I had before, but
Yeah, this is it's got all these stash changes, uploaded stream. This has been it's been messed up. Let's see. This is the spring one, right?
this one said like 2018. I don't know if anyone
This
else.
is 2020 spring. Let's see if
Yeah, the one you installed was 2018 spring.
yeah,
But
we don't want that one.
the one that we had previously was 2020 spring.
Oh, interesting.
Want
Because I downloaded it like before class today, and I'm pretty sure it was 2018 at that point.
yeah.
So how long?
I thought mine said spring 2019
Oh, okay.
when I downloaded it.
Is anyone else confused? I am confused here why this one's looking so funky. Let me open this. See if this one got screwed up too. Because I fixed this one. It's not fixed. Let me, that's not, this one maybe? No, it's not. Okay. Oh, wait, what did it just do? I'm gonna have to check that. The problem is I'm working on so many different machines and I'm using GitHub to store track my changes, and I think something happened with the last track changes. Okay, let's see. Right now if you download it the way I changed it, it will update this one. No, not the key. This one. And this one does not have it does not have 16A in there. Okay. I will, for 16A, I will put this in here. Let's do this. I will plot this on, let's see, can we get just a, I'm so glad we're doing this together and you guys aren't at home going, what in the heck is she wanting me to do? Okay, so let's do this. Let me share whiteboard. Okay. Okay, we'll just do this one by hand. So let's plot it by hand. You've got to plot it to be able to answer the question. So here's happy and here's fear. Okay, so we've already said that if you have two, on your y-axis, what always has to go on our y-axis? This has to go is our outcome variable, our dependent variable. What's our dependent variable in this one? It's how much popcorn in ounces that they eat. And let's go 5. This is a polished plot. It's a very great plot. I'm trying to draw with my mouse. Are you guys better at drawing with your mouse than I am? Because I suck at this really.
I'm impressed.
There. If I don't have my other one with the pen, so I'm mousing it today. Okay, so we've got, when your outcome variable always goes on your y-axis. Now we have two particular independent variables. We have the type of film it is. This is our repeated measure. And then what else do we have? We have our repeated measure factor and whether they're eating before or not. What is that called? Not our repeated measures factor, but our
independent groups.
Grouping.
Independent groups. We have the loading and the no loading. I'm just going to do it like this. So one variable has to be the x-axis. The other variable is what we're going to make our different lines by. Now you can do color, shape, line type, all of those things here. Now I'm going to do a square with dashed lines for my loading group. And I'm going to do a filled in circle with a solid line for my no loading group. There's my little key, my little legend for my plot. Okay, so we're going to make a plot for each person. So the first person in the happy film, how much did they eat? They ate 10 ounces of popcorn. And then in the scary film, they ate 12. And I'm going to use squares and dashes because, can I undo that? No. There's my dash one. Okay. Now the second person, they're also in this group. They ate 13 in the happy film and 16 in the scary film. Beautiful. Okay. Next person ate 8 in the happy film and 11 in the scary film. What trend are you seeing here?
Increases definitely towards with the
So
fear.
16 and 17. So for those that are in the loading group, they ate more popcorn in the scary movie. Okay, let's go down to the no loading. The first person ate how much in the happy film? They ate 26 in the happy film and 20 in the scary film. What do you notice there?
Opposite correlation.
Opposite. And the next person ate 19 in the happy film and 14 in the scary film. The next one ate 27 in the happy film and 20 in the scary film. It's perfectly to scale, yes. And then 20, right here, and 15. Yeah. So the question asks, does there appear to be about the same amount of subject by treatment interaction in each group? So the key here is in each group. So let's look at the first group, our loading group. In the first group, subject by repeated measure interaction. So we're looking at, is there much interaction in the first group? What does interaction look like?
They'd be crossed or
The crossing, yeah. So in the two groups, is there about the same amount of crossing in each group? Roughly. We
Yeah.
don't see anything wild. And then question B says, does there appear to be consistent amount of group by repeated measure interaction? Seems pretty consistent.
yeah.
Yes. Now, how would you describe this interaction? It doesn't ask you to do this on the homework, but there is an interaction here between type of movie and whether or not they ate. How would you explain this to someone? Like in the elevator, with no technicalities. Brian, what would you say? What's going on with loading and popcorn and type of movie?
Well, with loading, they eat less initially than they do with the, sorry.
Yeah, overall, those that had the meal before ate less popcorn. Yeah. But is that like across the board?
For the most part. Like there's slight variations. For example, like the last one in the preload, they actually ate slightly more the last time around. So.
So generally speaking, there is a main effect of loading. Those that eat before the movies tended to eat less. But what's the interaction? What's the effective type of movie? Does the type of movie make a difference?
Yes.
Yeah.
Kelly, you're shaking your head no. Why not?
Well, because they ate less popcorn when in our not loaded group. They ate more popcorn in the loaded group. And so it seems like it has more to do with whether they were loaded or not.
Yeah, if we were to average everyone out, here would be the average over here, and here would be the average over here, right? If we did everyone all together, if we ignored groups, there would be no effective, the two movies would be about the same, the overall. So there's no main effective type of movie, but there is an interaction. In the loading group, they ate maybe slightly more in the scary movie, but those that did not load, they ate less in the scary movie. So that's the interaction effect. How much they ate depended not just on whether they ate beforehand, but also on what type of movie. Movie doesn't have an overall effect if you collapse everyone together. But if we were to look at the average of this group, the loaders, the no loaders, and the loaders, it's very different for the happy film. During the happy film, the no loaders ate more than the loaders. That sounds weird. Those that ate beforehand averaged lower than those that did not eat beforehand. But at the scary movie, it's either the same, didn't matter, or we would say, or even that who would be less? The loaders would be slightly less, but there's a smaller gap. There's a bigger gap over here. That's the idea of an interaction. An interaction can be between repeated measures or independent groups or one of each.
Hey, Sarah, I
Yeah.
don't know why, but none of that made sense.
None of that made sense?
Like I get the graph, but I don't
Uh-huh.
see an interaction because I just see that loading is what's making the difference.
Okay, where did my picture go? Did I lose my picture?
Just because like I'm looking at this and I'm thinking if they didn't load, they ate more and then they decreased their eating. I mean it would flip-flop if you just had fear first and then happy. Do you know what I mean?
Mm-hmm.
So I'm not seeing like, it doesn't matter if it increased or decreased.
Okay, let's see.
Because happy and fear aren't ordinal. So it's just, so I'm just seeing that whether you eat before a movie is what matters.
Yes. Let's see.
So I guess I'm just not,
okay. Let me draw the average lines. If the averages are like this, it was like this. Like I'm not drawing every person, I'm just drawing the group averages, okay? Mm-hmm. So the group averages, so here there's a difference, right? We saw a clear difference on the happy film, there was a difference. The loaders that ate before the movie consumed less popcorn than the hungry people. But what about during the scary movie? During the scary movie, they ate about the same. An interaction is when the lines are not parallel. Are these lines parallel? No, we have a gap here and either no gap or a smaller gap over on this side with the scary film. So does pre-eating make a difference in popcorn consumption? It makes a difference in the happy film. It makes no difference in the scary film. So the role of preloading depends on which type of movie you're watching. Does that make more sense?
I guess I just need you to say that one more time. So the role of what?
Of pre-eating, of loading, pre-eating, the pre-movie meal. Mm-hmm. Those groups are not consistently different. The gaps are different.
Okay.
That for a happy movie, the pre-movie meal resulted in them eating less popcorn. But in a scary movie, it made no difference whether they ate before the movie or not. Everybody had about the same amount. On average, the two groups had the same amount of popcorn.
Okay, so can I say the role or the whether or not you load before the movie depends on the movie type as to how much you're going to eat? I guess I just don't know how to
effect of loading
on a test.
Loading was randomized. People didn't choose whether or not they were going to eat before the movie. That was a choice. They were either put into the loading group or they were put into the no loading group. That was a decision that was made by the researchers. So based on this, the effect of that pre-movie meal depended on what type of movie they watched. They watched a happy movie, the groups were different. If they watched a scary movie, the groups were basically the same. So the effect of preloading depended on what type of movie was watched.
All right, I finally got it. Thank you, because I just didn't know how to, like, if this were on the test, I didn't know how I was going to explain that.
Yeah, the verbiage is, an interaction is just the idea that there is a difference, there is a difference in the difference. So the two groups here are very different, and here the two groups are very similar. The difference in the two groups is not consistent. If the groups were consistently different, then we'd see parallel lines. Whether they were both up or both down, they would be the same distance apart.
So for number 5, then does that mean that it's the interaction is group by repeated measure treatment?
Yes. The interaction that we're talking about here is the group of subjects. Here we have group of subjects is either the square open box or the round filled in circly blob thing that I made. So there's a group by repeated measures treatment interaction. So yeah, in the next question, so let me go share the Canvas assignment. Back into that. Think. Okay. So this is item 2. Yeah. If you calculate a repeated measures ANOVA and then assign the subjects to subgroups to create a mixed design, the observed F ratio for the repeated measure factor may get considerably larger if there is a good deal of subject by treatment interaction. Okay, so now we're going to do a mixed ANOVA in R. So even the section B parts are in R. They're just with these little toy data sets. So in this exercise, we have subjects performing clerical tasks under 3 noise conditions. And I think that we've seen this before, but before we had 3 different groups of subjects. Here we have the subjects are doing all 3 noise conditions. But they're either assigned to one or the other type of task. So if we look at the syntax here, type of task is outside of the parentheses and noise is inside of the parentheses. This tells us that noise is repeated. So each person gets all the types of noises, but they only get one type of task. And the types of tasks are what? Mechanical or clerical, I believe. So if we go into R, so let's see, we load our packages. We do not need ls means anymore because it's defunct. And then read in all of our little toy data sets. So here is the task wide, and we're going to turn it into task long. So here's person number 1. They were assigned to do clerical tasks. So maybe they were addressing envelopes or filing folders into a file cabinet. And they have background noise. Under background noise, they did 10 of these tasks. Person number 1, still doing clerical. Under popular, maybe this is popular music, they got 12 tasks done. And if we go down here, under heavy metal music, they got 8 tasks done. So each person does these tasks in the background noise, popular music, and heavy metal music. So those are the 3 noise conditions. Everyone does the task, but they either are doing the clerical task or the mechanical task. So here's our summary statistics. What does it look like? People doing clerical tasks. What pattern do you see with the eyeball test? What does it look like? When do they do more or less? The clerical tasks.
Popular music.
Popular music, they get more done. Heavy metal, they get less done. What about mechanical tasks? Do we see the same pattern?
Much more efficient in metal. Do more during metal.
Overall, they're getting more of these done. Maybe these are quicker things to do. I don't know. But they're doing the most in the heavy metal. So here is a plot. This kind of plot is called a profile, a person profile plot or a profile plot. Each person's profile or all that person's data is given with a single line. So here we have the clerical tasks are the coral circles and the teal triangles are the mechanical tasks. Are the shapes of those lines the same? Are they same in this, if they're the same group? What about in the teal group? Are they more similar to each other than the red circle groups? We can see that there's group-wise trends. Is everyone the same in the same group? Identical pattern, identical levels? No, there's person-to-person variability, and there's person within group variability, and person over repeated measure variability. What we want to know, does the type of task make a difference? Does the type of music make a difference? And or is there an interaction? Okay. So this is a person profile plot. It plots each person is a line. The second plot is often called a means plot, and it's only plotting the means. And we learned how we can add a second stat summary with the function equaling the mean and the geom equaling quote line that connects the dots. Oh, but we have to add group equals 1 into the aesthetics, or group is equaling type task. We want a line for each type of task. There we go. There's our means plot. Notice here we have each person. Now we want to collapse all the teal lines into one and all the coral lines into one based on the average. What do you see with those lines? Are they parallel? Nope, not even close, right? With background noise, they're overlapping, but what about for metal music? They're diverging, and what about for popular music? They're coming back closer together. So it's like they're the same, they're going away, and then they're coming back together. Okay, so let's do the mixed ANOVA. Okay, so to do the mixed ANOVA, we're going to save it as fit tasks. So we're going to save it as. Okay, so what do I start with to run my mixed ANOVA?
Tasks long?
We need the data set, and the data set is tasks long. And then what do we do with the data set?
Type it in.
Type it into, what do we use to do an ANOVA? Any ANOVA?
Package.
AFEX, AOV4. Now I didn't take very good look at that data set, so I'm going to highlight the name of the data set and do Control-Enter on my keyboard so that I can see my variable names. What comes first in the AFEX ANOVA?
Continuous variable.
Our continuous interval ratio score that we're comparing, which is which variable name?
Completed?
We're going to use completed. How many tasks they completed. Is it completely continuous? No, it's a whole number, discrete number, but it's continuous ask. Then what comes after the name of the dependent variable?
The type of task?
Tilde
Or-
wave, and then we put the grouping variable, which is task type task. BYP underscore task. The independent grouping variable goes outside of the parentheses, and then inside of the parentheses, what do we put?
Noise?
The type of, or the variable that is the repeated measures factor, vertical bar, ID. And data equals dot to pipe the data in. They could have done an experiment where everyone did both types of tasks, but only under one type of music. Or they could have had everyone do every combination or only one combination. But in this scenario, each person only did one type of task, but all three music types, noises. So that's why noise is inside the parentheses, because everyone had all three noises, but the type of task they only had one of, so that's why it's the independent grouping factors outside of the parentheses. Okay, now up in here it says some other information. I want to show you, if I do some, I'm just going to do this much, and then I'm going to do the name of the model in the same chunk. I want to show you, no, summary. Okay, so when you do summary of the model name, that gives you the three parts of the output: the assuming sphericity and then Munchley's test of sphericity. In this test, in this one, if you look at the test of sphericity, what do you notice about Munchley's test of sphericity? Is it significant? It's significant, but it's right there at the 0.05 level, right? It's just barely. For this problem, we are going to request no corrections for the violations of sphericity. And the way that you do this is after you say data equals dot, you have to do comma, enter, Anova table equals, and then you can put a list of options. The first list we're going to put in there is correction equals none. This overrides doing the correction. I mean, we could argue that you should do the correction here, but I'm going to override out of it, okay? And the second thing it says here, we're going to go ahead, and it's missing a close parentheses, but we're going to request both effect size, the generalized and the partial effect size. So after you say correction equals none, after the quotes do comma, enter, ES for effect size equals concatenate the generalized effect size and the partial effect size. We want both of them to be outputted. Okay. So things that are different than we've done before. We have both an independence grouping factor and a repeated measure, and I've asked it to not do the greenhouse geyser correction for sphericity violations, and I'm asking it for both of the types of effect sizes. Now, I know it says in here to add the $AOV, but I'm not going to ask you to do that. Just put the name of the model. And you get the 3 effect sizes with the 3, or the 3F statistics with the 3 effect sizes all together. Give me a thumbs up when you get that to work. 2, 3, 4, 5, 6, 7. No, Melissa?
I didn't get it to work.
Okay. So did you get it to work? Did you try it without doing the Anova table?
Yeah, it worked when I did the summary.
Do you have 3 closed parentheses at the end?
Yes, it says unexpected close parentheses.
Okay, so you probably look for your parentheses. So there's a first one before the formula.
Yeah.
Parentheses starting and ending around noise vertical bar ID.
Yeah.
And then after the word list, there's an open parentheses.
Yeah.
And then no more on that line.
Oh, there's my problem.
Okay.
Okay. Now it ran.
Okay, perfect. Okay, so how many F tests did we get? 3. The first one's for type of task, the second one's for noise, and the third one's for the interaction between type of task and noise. So when we look at our Canvas assignment, where did Canvas go? Here we go. We are asked to, oh, Canvas, go over there. I like you over there. So Canvas asked us to put in, now it says the AOV, but we're not going to do that AOV. Okay? So report the results for the between subjects effect. Which one's the between subjects effect? The difference between subjects. Which one of these 3?
Type task?
Type of task, because subjects were either one or the other, they were never both. Okay, so what goes in our F statistic? I highlighted it, you can't see it now. Degrees of freedom are
1 and 8.
1 and 8. And the F statistic equals 7.87. Oh, I need a decimal. That won't work. What's the within subjects factor?
So the degrees of freedom are 2 and 16.
2 and 16, because this is the noise, because we repeated within each subject noise.
And then 2.58 is the
Yep. And then the group by repeated measures interaction would then be the type of task by noise interaction. So what is significant? Is the between subject effect significant? This first one? Yes. Is the within subjects factor significant as a main effect? No. What about the interaction between the two?
Yes.
Yes.
So we use the p-value to evaluate that, not an F critical value.
You can either look up an F critical value, but that would take looking in the book and finding a value.
Okay. Yeah, I just was.
Or you can just look at the p-value. Yep.
Got it.
Both of those methods work. We'll go with the p-value since it's got spit out of R. That's handy then.
I like that.
I do too. Okay, so now we're going to look at the effect size. So we're going to look at it for the, it says the main effect of type of task. Type of task. What is the generalized effect size?
0.462.
6.2. Let's see. Don't anyone push check your answer until I do, because I might only want it to 1 decimal places. And what's the partial eta squared?
0.496.
496. Oh, it's going to take it. Okay, that's okay to 3 decimal places. I was nervous that I hadn't allowed for that. Okay. So based on the general eta squared, does this look like a large effect? Now you don't have the cutoff sitting in front of you, but this is akin to the general eta squared. This is like 46% of the variance. That's pretty big. I think the cutoffs are like 0.8, 0.16 for small, medium, large-ish.
Mm-hmm.
Okay. How are we doing on time? Ooh, we're not going to get that article done. Rats and mice. I'd rather, this one's just about the same way. I'm going to skip this one and let you guys work on 4, okay? Because it has you do another mixed design, get out the F values, what's significant, what about assumptions of sphericity? Okay, I think you guys can do that one. 5, yep, same thing. 6, yeah. But then we end up having some APA write-ups. Okay, this has APA write-up because this is an APA journal article. Let's look at an actual journal article, shall we? Okay. I really do want to look at this one because it really is cool. It really is. Okay, so again, if you want to follow along, if you share screen, you're gonna see this, but this is on the home page of our class. It's the 3rd thing down here right before our learning curve. And this should take you, well, it'll download the PDF. I'm gonna make this bigger. I can read this. Okay, so this is cool because this was a replication study. So these authors at York University tried to replicate as close as they could, another study that was done in 2005. And this one was published in 2012. So this, and the publication dates ended up being 7 years apart. So what they wanted, they're trying to replicate a landmark study. Remember, one study the truth does not make. We need replication because you can never rule out a false positive. So they're looking at benefits of this positive psychological exercises. Specifically, they're looking at this thing called 3 good things. And it's an exercise that they do. The original study looked at 2 exercises, the 3 good things and using your signature strength in a new way, these exercises, to see if they had any long-term effects on 2 outcomes, depression and happiness. So they tested these exercises here. They're supposed to improve. So they did not test it using the same methodology except for improvements to the control condition. So they improved the control condition. So it's not an exact replication. And they added a second positive placebo to isolate a common factor for looking at positive controls. So this is a controlled design. We have an expected control and a positive placebo. So there's 3 groups here. So we have this PPE is these positive psychological exercises that they're doing. There's a lot of information here, but that's the main thing is we're looking at these positive psychological exercises and how they affect happiness. So you notice we've got our objective. This is the little abstract with just like a sentence or 2 each for each of these, you know, objectives, designs, results, conclusion. But then the bulk, here we have kind of the background. They explain about the original 3 good things, using your strength, these exercises. They originally one looked at 1 month, 3 month, and 6 months. So repeated over time. And so under methods, in the methods section, notice the subsections. First, we have the participants. So their initial sample, they had almost 1,500 participants, ages 18 to 72. They got them online, and they give some demographics. Now, check this out. What do you guys think about how they did the summary statistics in line? Now, instead of X bar and S, if they're doing it APA, it should be capital M and SD, and those should be parenthesized. But oh, it is in parentheses. They just didn't use the right abbreviations. Okay, we'll give them. All right, so after they said these are the participants, the next subsection or in here, it tells about how they gave them money and they entered them in drawing to get them to keep participating. And then here are the measures. So they measured, we're looking at happiness and depression, so this is how they were measured. And here's the procedure, how things went about. They had an expected control, a positive placebo group, and then the 3 good things group. This is the group that they're really trying to show is different. And then there's the signature strength. So there's 2 like treatment groups and 2 placebo groups basically. And they had everyone doing 10 minutes a day on these things. And then they emailed them reminders to fill out their questionnaires at 1 month, 3 month, and 6 month follow-ups on both. And they did both the happiness and the depression things. In the results section, we have attrition. Guess what happened to their participants over these 6 months? Oh, not everyone came back. So of those that filled out the initial questionnaire and were assigned to an X, we had these 1447. Of those, 334 completed, or only less than a quarter completed everything. Less than a quarter. This is real life research. What does that make you think?
Well, you have a substantial dropout rate.
Yeah. So it says t-test shows that those who dropped out by 6 months were at baseline more depressed. The dropper-outers were the most depressed people and the least happy people. If you compare the dropper-outers to the stayer-inners, they were different. So if you do an Anova analysis, you can only keep in and analyze the completers. Are they going to be representative of everyone? No. So is an Anova method appropriate? Probably not. They did say dropout rates were not significant by condition. This is a chi-squared test. This is what we're going to learn to do on Wednesday, our last thing we're going to learn to do. Notice they have t-test. Did they put the t-test in here right? We got a t with degree of freedom equaling a 2-digit number, 2 decimal place number equaling a p-value to 2 decimal places. Is that pretty good? I'd maybe go 3 decimal places on the p-value, but that's not so bad. And this one, notice, is less than 0.001. They did pretty good with those results. Okay, so on the replication, okay, so here, they say that the original analysis that the original paper in 2005 used, a repeated measures analysis of variance. And see, the first time you say analysis of variance, you have to type out analysis of variance, and then you can put in a parentheses ANOVA. Then from there on out, you can use the ANOVA acronym. Okay, so that's always with all acronyms. So they are going to use an ANOVA method. Now, I want to point out, what do you see at the bottom of this page? It's a footnote. How big is this footnote? It is ginormous. Look at this whole page. Look at how big the footnote is. Now, I can almost guarantee that what happened is this group of researchers wanted to replicate this research, and they said the original paper did a repeated measures ANOVA, so we're going to do that. So they went out and they did their data. But when they actually gathered their data and they tried to email and get people to come back and finish their follow-ups, people didn't. And they said, what do we do? I want to replicate this result, but my data doesn't really work well with the repeated measures ANOVA. What should I do? Should I use their method to replicate it, or should I do a better method? So my guess is that the authors here did the ANOVA to replicate the original paper, and then they submitted their journal article to the journal, and reviewers said, hey, if 76% of your participants dropped out, it's not a good idea to only analyze the 24% that finished, especially when you can show that those finishers are different. They're already happy and less depressed. So they have this footnote, which is probably coming from a response to a reviewer. So let's read it. A drawback of repeated ANOVA statistic is that participants with missing data points are excluded, which is particularly problematic given our high attrition rate. So what's another option? Multi-level modeling, which they conducted in SAS, which I teach in R, you can even do it in SPSS, and using maximum likelihood estimation was performed as a sensitivity test. So what they end up doing in the remainder of this paper is they present the results of the repeated measures, or actually it's a mixed design ANOVA because they have different groups and everyone's over time, repeated over time even in the groups. But off to the side, they reran the analysis with multi-level modeling to see if they get the same results, which they show here that they get the same, well, pretty much the same story being told. And because of that, they say these results, and they go on to all this stuff showing the multi-level modeling, which you can use your partial cases, says these results mirror those obtained with repeated measures ANOVA presented in this text. Now, I would prefer that they had put the multi-level model in the document and put the ANOVA in a footnote, but for whatever reason, they've done it the other way around, probably for one of two reasons. One, repeated and mixed design ANOVA are more commonly known because they're taught in every intro stat class, like you're taking right here, right? So every researcher should have had some familiarity with them. And number two, the original paper uses an ANOVA method, so they wanted to replicate it. But they have provided this glorious footnote about saying how they redid the analysis with multi-level modeling, and it tells pretty much the same story. So I thought that was great. Okay, next page. All right, what do you guys think about this plot? I hate this plot. I want to remake this plot so bad. What kind of plot is this? What would you call this?
Well, it's like a bar chart. I mean, it doesn't.
It's a bar chart, but what's the rule about bar charts?
It's set up like a histogram.
It's set up like a histogram because the bars are touching. But notice the y-axis. How far down does it go?
Oh.
What's the rule about when you do bars?
Has to go to 0.
Bars must go to 0. What are the tops of these bars showing? Read the note underneath it. Figure 1 shows, what's that first word? Averages. Those bars are showing the averages. Instead of using bars to show the average, they should be using points like we've been doing. Points and maybe having standard error bars, but they should have points. Now, what do you think these numbers up here are?
That's got to be Cohen's D.
They're Cohen's D. Cohen's D are comparing 2 points. So what are they comparing? 2 averages. It's each of these gray bars compared to the, says effect size, note, effect size is noted where means different from the baseline. So they're comparing each of these bars back to the baseline. What do you notice at baseline? The 4 groups are, now this is the happiness scores. At baseline, the 4 groups are about the same happy. What about at 1 week? Are they all the same happy? It's showing that the gray and the black bar have become more happy. Do they stay more happy? By the end, who's more happy? Who's happiest? This is the placebo group right here, the white one, the early memories. Yeah. What do you notice about these group sizes? These are the complete cases, by the way. The group sizes are?
They're definitely unequal.
Not equal. Another reason Anova would not be the best choice too. But here's another takeaway I want you to get as our time together is almost over. All models are wrong. Some models are useful. So even though the assumptions of Anova, we can't use all, but we only can use complete cases. We're supposed to have balance in our design. Even though we might violate some of those assumptions and requirements, we still can tell a story. And the story that gets told here with the Anova method ends up being the same story that a better model ends up telling too. So I want to stress checking assumptions, but know that even when you violate assumptions, sometimes methods can still tell the appropriate story. But you don't want to bury your head in the sand about assumptions. So it's always good to check another method. Okay. So let's see if we can figure out what this means. So let's see. Now that we know what we can do. An overall repeated measures ANOVA was conducted. 4 conditions by 5 time periods. 4 conditions, everyone's in one group, 5 time points, baseline, 1 week, whatever the follow-ups were. Is this a repeated measures ANOVA? We have 5 time points, but we also have 4 independent groups. So I would call it a mixed design ANOVA, but you will see frequently people will call a mixed design ANOVA, they'll still call it a repeated measures ANOVA. Even though it has that additional grouping factor, they will still call it repeated measure, even though it should be called mixed ANOVA. So I wanted to point that out to you. You will see that a lot. So what do they say? A significant main effect for time was found. And then here we have comma, this is APA style, right? And then it has our F value with 4, 337 degrees of freedom, equaling 8.53, p-value less than 0.001. And what do they have after the p-value?
Got the partial eta squared.
A partial eta squared. And what does this partial eta squared tell us?
It was a medium effect size.
That's a pretty moderate effect size for, what is this for? This is for time. There was change over time, a moderate effect size. So they say the main effect for time, and then they say what it means, indicating that participants increase. Notice when it's an effect, they don't just say change, they say which direction. They increase in self-reported levels of happiness over time. This is well done. And then they say a significant time by condition interaction was also obtained. And then we have our F value, our P value, and our partial eta squared. How big is that interaction? Small, medium, or large?
Small.
That's moderate. See, small. I would say small. It's about 3%. But this shows varying changes in happiness over time. So if we look at this group, the white group, how much do they change over time? It shows an arching here if you look at the tops of the bars. However, notice none of these bars have Cohen's d. The Cohen's d are shown if the p-value is significant comparing back to baseline. So really, there's no significant change. Even though we see an arch, it's pretty much essentially flat. What about this light gray group? At first, there's no change, and then there's change. Now.
So on this one, since they had an interaction, like with a mixed ANOVA, it's okay to talk about the main effects being significant too. Is that only with one-way ANOVA where?
Or two-way ANOVA, independent
two-way.
Generally speaking, if we turn back, I know it's only been like a week or two, but really it's been a long time content-wise. When you have an interaction, you should talk about the interaction more than you talk. When's the only time you talk about the main effect in the presence of an interaction?
When the interaction wasn't significant?
When either the interaction is not significant, but if the interaction is significant, there is sometimes when we're allowed to talk about the main effects. I'm trying to pull up the slides really quick. This is two-way ANOVA. Chapter 14. These are slides, right? Here it is. Pull it up. Oh, no, that's the 14 example. Not the 14 chapter. There it is. There was a slide. The same thing, because the same thing applies. It is recommended to only interpret the main effects if there is no interaction, like Melissa said, or if there is a significant interaction, you can, with extreme caution, if the interaction is small. Was this interaction small? Yeah, the Cohen's d was 0.03, and there is an ordinal pattern in the means. However, you must report all the main effects and interactions regardless of statistical significance. You're still going to report them. So in this paper, where did it go? Where did it go? Haha. Is this an ordinal interaction? The white group is pretty much flat. All the other groups are pretty much going up. That's it. So the order is staying the same. It's not very much crisscrossing. Now, it's really hard to tell that without connecting our means, which they didn't do because they did this bar plot instead of a point and line plot. On this page, they show this is all the averages and standard deviation, which they're using X instead of X bar, which I don't understand why they did that. I want to take this data and make the correct plot to show you how much easier it is to interpret, but I've never found dead time to do that. But so yeah, so usually we would focus on the interaction, not the main effect. But here we have a small interaction and it is an ordinal interaction. So thus it's okay to talk about the main effect too. And then what do? Planned contrasts. How did they know to plan these contrasts? Because they were basing it on replicating prior research. They knew what they wanted to have their contrasts be. We're not always in that. So they were conducted for the happiness scores at each follow-up within each group. And so here are the P's and the Cohen's d for all of those. So participants in the expectancy control group tended to increase in happiness at week 1. So they went up with a Cohen's d of 0.1, which is small. But then they returned to baseline at 1 month, 3 month, and 6 month follow-ups. So that's those white groups. Notice how it went up but then it pretty much came down to back where it was. That's what they're saying there. So they're doing the follow-ups, white groups times to other white groups time, and then light gray to the other light grays, dark grays to the other dark grays, and then black to the other blacks. So they're doing pairwise within each group. That was their planned contrast statement. So that's what they're showing here. And then in summary, they found the results were mostly replicated, and these positive psychological exercises surpassed the effect of the expectant control group, but not the positive placebo. So all three, these two, the dark gray and the black, are the groups they're trying to compare to. Then they both outdid the placebo group, but not this positive placebo group that they added that the original one didn't have. And this is where they just had to think about positive past memories of your life. So anyway, so in summary, I wanted to show you some good, some bad, and repeated measures Anova in actual application to show you how things can be written up. And this is an Excel plot. I can just tell by looking at it. This was made in Excel. Anything you're going to make in R is going to far exceed this. So please don't make this kind of plot. But at least they included all the means and stuff, and they did a pretty good job of writing up the Anova results.
Sarah, just a quick question.
Yeah.
When we have to review like the APA results and methods, are we just going to be reviewing for formatting, or like are you
actual
like you just putting the wrong numbers or something?
All of it. The
Okay.
numbers, the numbers, I think on the test, I'm pretty sure I put the right numbers, but I might have said something was significant when it was not significant. I might have said increasing when it should be decreasing.
Okay.
So those are the kinds of things you'll have to edit.
Okay.
Yeah.
Good to know.
Yeah. I feel so bad for you guys. You're gonna just hang in there. This time next week you can unless you're starting 7610, right? Who's doing 7610 again? Yeah. Oh, you guys.
Yeah,
You'll be fine. You'll just be so tired.
Yeah, I was going to, but after this class, I said, you know what, I'll take it in spring.
Spring,
I know I might be there too, because I have another class on top of this where we're writing our lit review.
Yeah. You guys are completely capable, but you've got to feel worn out at this point. You've got to. Okay. All right. So we're way out of time. 7 minutes over. Office hours tomorrow at 7. Email me questions on the homework in the meantime. We should be able to record them because I don't have to go to the pool anymore, so I can be at my house and upload them. And homework 15 should be about done. 16 you're at least got to start on. And then the test, that's for Wednesday. Then by Friday, read chapter 20. I'll send you an announcement. I'll look right now. There's a little tiny bit in chapter 19 you need to read, but not all of chapter 19. It goes way overboard from what we need. But we do need chi-squared tests because they are used a ton.
Can you go back to that? Oh, no, go back to that. I wanted to look at the APA for the contrasts that they did.
The contrast statements?
Did you already talk about that and I just missed it because I was thinking of something else?
Yeah, so they said here,
they didn't report the T on the contrast or tell you.
On the contrast, they're only reporting the P's and the D's. So
are they doing a different type of contrast than what we do?
No, they're doing T values, but they're not typing in the T values. They're only giving the P values. And they didn't say, they said they're doing planned contrasts. I think they're doing pairwise contrasts. Is this D at 25 or is that 0.25? That seems a little, I think that should be 0.25 and this one's 0.20, I think. We did not do Cohen's D on pairwise, but Cohen's D you would just take to the two averages. So here it's comparing for the expected control group, increasing in happiness at week 1 compared to week baseline in week 1 You subtract the averages and divide by the standard deviation. R doesn't do it automatically for you. You can get the means with the EM mean statement, and you can subtract them easy enough and divide by the overall standard deviation is usually what's done. But it doesn't say, does it say anything here about multiple comparisons? It does not say. So I'm thinking they did not do any corrections for multiple comparisons, which even planned you should be doing some.
Because they did a ton of pairwise comparisons. Like every one of these is a pairwise comparison, isn't it?
Yeah. Well, here, if we've got 4 groups, 5 time points, that's 20. So if they didn't do all pairwise, would be any one of the 20 compared to any one of the 20. They didn't do that. They only compared each of these times, 1 week, 1 month, 3 months. They only did 4 comparing back to baseline. They did 4 pairs per group, so they only did 16 pairwise tests. But 16 is a lot.
Yeah.
Yeah.
Okay.
A multi-level model would have been a much better way to go, because then you don't have to worry about homogeny variance sphericity, because they haven't addressed that here. We just have to take their, yeah. Notice, did they ever say anything about sphericity, homogeny variance, normality? Usually when you report ANOVA and repeated measures ANOVA, mixed design ANOVA, you usually cut that part out because you don't have space, and it is assumed as a professional you would not present these results unless you had established that by virtue of not saying anything about the assumptions, that the assumptions were fine. Always makes me wonder. Okay. That's why knitting your R document and providing it as supplemental material gives interested minds the ability to check that and know that you did that, because there's not room in here. This is a long article as it is. Okay. Way over. You guys, you've got places to go, things to do. Okay. Kimberly, do you still want to stay after?
No, you answered my questions.
Okay. Anyone
Oh,
else?
except my R is not knitting. Maybe
Okay.
just for a quick second.
Okay, let me stop recording.
Okay.
And then we can, if anyone else wants to stick around for issues, then you can. Let's see, recording.